Yeah, again, thanks for coming for the last tutorial of this series. So different from the first three tutorials, this tutorial is composed of the three very different topics. The first is about like custom libraries, second, Teensy audio system, and the third is the ZaberMotor system. When we talk about custom libraries, so the first thing you came to your mind if you have some experience in programming is, you probably just mean packaging some codes, which you are going to use again and again into some functions and in the object-oriented programming language into some like classes. And then we can like write functions and classes in our code. But if we just use it really again and again, and also across different projects, so like I have protocol 1, I have protocol 2, I have or different codes, then we want to like put those super commonly used codes into a package or library. So that applies to both MATLAB or C++ like here in Arduino, as well as like Python, you name it. We are all on the same page about that. So therefore today, the focus is like what kind of code I want to put into libraries, and more to be more specific. And also I want to provide a series of examples in the context of rig building and behavioral controls, so that so to kind of open up our mind, our imagination of what kind of like repeatedly used code that can be. Okay, we need a code editor, a text editor, a better editor than the Arduino IDE to edit those C++ libraries. Yeah, so the program I recommend is called Visual Studio Code. So Visual Studio could be a familiar name to you that has had a long history and is the power horse of programming software in the Microsoft world. But over decades, that software has become very bulky and cumbersome. You just install a million kind of dependencies and stuff in a computer in order to use it. The visual, and so therefore, in the last few years, they released the Visual Studio Code, which is a very lightweight, kind of smart, but at the same time still modern code editor. And furthermore, it supports all sorts of languages. You name it, like C, C++, F#, C#, Java, Python, anything. And it also has a whole array of so-called extensions, or basically plugins, to even implement many functionalities for like very specific platforms. Like I can write Arduino codes in here, and I even can compile Arduino code, and even can upload Arduino code to Arduino boards directly from the Visual Studio Code, which means you can basically replace or familiar Arduino IDEs using Visual Studio Code. So that comes to, as far as I see, like 3 levels of using this Visual Studio Code. And the first thing is pretty easy. You just install it and basically use it as a simple editor, not very different from this. And here I have opened this, and I'll close the welcome page and the file. I'll open I'll add a folder to our workspace. And here later, the library I'm gonna talk about more in detail is called ManyRig. The name doesn't matter. I just want to say, like, the first thing you can use this editor is basically just look at our libraries, right? Or look at any kind of libraries. So this is the first level, and without needing you to do any setup. And I would say the second level of using this is to actually take advantage of smart functionalities of this code editor. For example, like here I've defined a function, and then like in C++, the C++ is kind of weird that you have in something called a header file, a .h file. You first have to say what function and variables I want to have, and in a separate file, that's called CPP files, or in C language it's a .c file, is where you actually say how I'm gonna implement that function. That's a digression, but here, like there are links between the contents between the two files, right? So here, this is a declaration of a function. I can right click and say go to definition, and you see the code editor kind of recognizes the links, and so it directly kind of directed me to the implementation of that function. And also, sometimes, actually oftentimes, we need to rename our variables, and that's the formal term for that is like refactoring the variable names. And maybe because over the time we found that the name no longer fits the role of the variable, or there's some conflicts, or we want to optimize it. And then in MATLAB there is something that within one page of code or in one scope, and when you change something, you can shift enter to kind of replace all the variables of the same name. But if you fully set up this code editor environment, and there's a function called IntelliSense implemented by a plugin, and it actually recognizes all the usages of a given variable across the entire program, not just one file, across files, all the related things. And you change one place, and the IntelliSense allows you to refactor all the usages. So that's just two examples, and that's the second level of using this Visual Studio Code IDE. And then the third level of using it is basically turn this into a Arduino editor, Arduino IDE completely. So that requires you to install the in addition to the C++ plugin and also the Arduino plugin. I can show you here. So I have installed the C++ plugin and also installed the Arduino plugin. And then after that, after some setup, you need a kind of a JSON file to say where I'm installing my Arduino programs at, and what kind of compiler and what's the IntelliSense mode I'm going to use, and so forth and so on. And then and then for Arduino code, you can actually do compile and upload inside here. So for a more detailed tutorial, I will post a link. And this is a tutorial from SparkFun. They have a lot of useful, very well-written tutorials. It will just walk you through those. Yeah, so I spent a lot more time talking about this because I think if you want to get on some advanced programming, or one day start writing your own libraries, or even just look at my library and trying to modify it, having a more colorful, meaningful, informative code editor will be tremendously useful. Right now, let's jump into the first example of a custom library. So before explaining the content of this library, I want to invite you to think about a situation here. So so this is a situation that actually happened in Jeremiah Cohen's lab, but at least not so much in our lab so far, which is they have a lot of rigs, and they use a very similar, or oftentimes it's the same behaviors across different rigs. And then, of course, if you are running the same behavior, then you use the same behavioral code, right? The same Arduino code to implement the behavior. But the problem is, different rigs have different kind of hardware connections. And for example, like in one rig, the leak detection pin is connected to pin 5, and in another rig, the leak detection pin is connected to pin 9. And then, okay, so then you may say, oh, that's easy. So on one rig, I just changed the Arduino pin definition. Here, I'm just pulling out a kind of random random code, and like, you know, after the include, and here before the, and here is where we kind of define a bunch of global variables, and often including the pins. We just in different rigs just change the number of pins. Okay, but then here's a problem. So imagine like someone is trying to update a version of the behavior, and they start changing the code. So, and they commit to GitHub, and then all of a sudden, all the other rigs need to kind of take down that code and then change all the pin numbers. And sometimes it's more than just pin numbers. Like, for example, like how the leak detection is done. Like maybe some rigs use conductive detections, some rigs use capacitive detection. Like the underlying codes are basically different, or they're just different. They're not the same code. And then you have to do a lot of adaptations for a simple update. For example, in maybe just about a simple logic during a minor modification in the behavior control. And furthermore, if someone want to write a new behavior protocol, and the person needs to go to the rig and figure out, oh, which pin is the water valve, which pin is a LED, and which pin is this, and which pin is that. And then now you see things become complicated and therefore error prone. So, and this is actually an opportunity for us to write a custom library to resolve that problem. And the custom library will hide the pin number away from the users, and also like take care of the low-level hardware controls. So what the user, I mean, when I say user, are actually the programmers who like write the behavioral code and to implement the behavioral logic. And so basically these kind of rig-specific custom libraries handles all the pin configurations and hide away the low-level hardware control. And all the users only need to know like the functions, function names that's specific to leak detection or opening of a water valve. Okay, now we can look at this specific example. So the class name is ManyRig. This is a bad class name. I wish I kind of change it. Maybe I will change it to like rig1. So when everybody will know, oh, so this library is specific to the rig1 library. Well, it applies to our rig1. And here we are looking at the header file. Again, header file basically says what kind of variables and functions do we want to have. Oh, so by the way, this is a class. So this is a ManyRig class. In this class, we have these variables. They are all about pins. So you see we have leak detection pins and a pin that picking up some noise from the air. So we can have a seed for random number generation, water valve pin, high-speed video frame trigger, and synchronization, camera trigger, wave surfer trigger, and audio triggers, and also a servo controller pin. And for, but in addition to the pins, we also have those kind of basic hardware level input-output functions, like one that detects whether a leak is present or the leak port is being contacted or not, and then to send out a trigger for the auditory cue, and deliver a water reward each by this duration in milliseconds, and send out a TTL, for example, for a synchronization purpose. And it's actually more than that. So you can, you know, there are something that we frequently use during behavior control. For example, we have like 3 trial types or 4 trial types, and then we want to like select the different trial types based following certain probability distributions. So like this is very commonly used in many different places. I even write a choose function that by providing the probability distribution in the form of a vector, and like of course how many choices we are going to make, and it basically output a number that represents the randomly selected index of choice. Yeah, so just a little glance at the implementation of some of them. For example, like here, so we are looking at the .c++ CPP file, and here we say in this rig, like leak detector is this, and you see the pin assignments here, and then also we handles the mode of the pins, right? In our final Arduino code, if you look at the setup, it's pretty clean. I mean, there are a lot of stuff going on, but it's pretty clean. And you see it mainly handles the very high level kind of configuration. So this is about link port and then some position initializations. You don't see anything about like initializing a pin and to configure it as an input or output. And so that both simplifies the code, but also kind of maintains the integrity here. So, and the implementation was already done when initializing an object of ManyRig class. And and here you see for the isLickOn function, there is really just a single line that you like goes like digital read, and to see if this pin has a high voltage or low voltage. High voltage being like 3.3 or 5, and low is like 0. And similar for others, like deliverWater, just standard three lines. I turn the voltage to high at this pin and keep it at high for this number of milliseconds, and then digital low. Yeah. So yeah, again, please ask me any questions if you have. Yeah, so this is the idea. And then like, for example, like Rajan uses a 2-photon rig, and then you may or may not have the same kind of pin configurations that I do. And then you can basically copy the entire folder of the ManyRig and call it like rig 5 or 4. I actually don't know the rig number of that. And then you can keep everything in the header file the same, well, except the names perhaps, and then just kind of change some of the implementation, like the pin numbers and the specific ways you want to do it. For example, for the 2-photon rig, which we may not have an immediate plan of doing simultaneous electrophysiology, then instead of this kind of a conductive leak detection, we can use a capacitive leak detection. And then here you just need to change how this function is implemented here, and all the behavior codes on the top remains the same, right? I hope this is a kind of a unique examples about like what custom library can be useful for, other than just simply kind of wrapping up some very commonly used functions. And so the second example I'm going to talk about is this interval class. So I can write this class outside somewhere else, but I feel like the interval class serves kind of similar kinds of function purposes as the choose, which means there's something something that's useful for implementing the behavior control logic, and then so I just put it in here. So whenever we kind of include this, and then the interval class will also be automatically included because they are in the same header file. And so, but what is this for? So the interval class is used, for example, I'm pulling out the sequence leaking task protocol at the end of each trial. So we are going to figure out what is the intertrial interval it's going to be. and in my task, inter-trial interval has a part with fixed duration, and it has a part with a randomly sampled duration following an exponential distribution. Of course, you can certainly just write the code here, but I thought that that's going to be a very often used and general purpose function. So I wrote a class here. And if you look at the properties here, we have a fixed duration and the mean value of the random duration and the upper limit of that random duration, because you can sample like very, very long time duration from the exponential distribution, though with kind of low probability, but it still happens. So we need to cap it. And also you may also not want to have a super short random short limit. And so at least those are the things we want to have. And then here, this is the code that implements it. So it samples from exponential distribution, and you really don't need to worry about the math here because I've put my thought into it and I make sure that my math was correct. And so then you or other people can simply just use this interval function to generate, to sample inter-trial intervals. So for example, here, ITI is an object from this interval class, and .nextRandom really just updates this value, right? So every time nextRandom is called, and this number gets updated into a new one, which is basically a new sampling. And to retrieve that value, and here basically ITI dot random duration, then you get it. And of course, ITI dot fixed duration is always a constant because it's fixed. Yeah. Anyway, so that's a quick second example. Basically, an extension about the idea, just like the choose function. So there are many useful functions for behavior control that's already written by third party. And here I want to highlight just one of them. Well, at least for this part of the tutorial, I would want to highlight one of them, which is called IntervalTimer. And then again, using the SeqlickSound code as an example, and here we say IntervalTimer and then number timer. So this is, we kind of created an object here. Oh, by the way, so you see the ManyRig class was used in here. So ManyRig class name, and the rig is the object name or the variable name we denote it to be. And also here interval is here, and ITI is the variable or object name for that. Okay, back to the interval timer. The reason I want to bring this up because it's really shines light to very important concepts in Arduino programming. It's not just about this class. So different from our computer, different from our phones, we know like our computer and our phones can execute many programs at the same time. For example, I'm running Zoom here, but I can still use the Arduino and browse website, and a lot of things can be done at the same time. Same for our phones, but it is actually not the case for the microprocessor, for most microprocessors. But that's obviously something we do want to have, and it is important to have, at least even if it's not like processing two things really at the same time, but at least if they can kind of quickly jump back and forth is also good. So in terms of quickly jumping back and forth, we have already seen an application of that, which was explained in the first tutorial when we were talking about, I think it was the first, when we were talking about the satellite library. Although it's not a part of the satellite library, it's a part of the official Arduino function. So here we see the attach interrupt. So set up external interrupt and callback functions. So this is about licking. When our code is being executed during the behavior protocol, but a mouse licking can happen at any moment in time. And whenever that happens, the program wants to respond to that and kind of register the kit both internally in the hardware, but also kind of send a command to the computer. And that's why it's called the interrupt. The external lick that triggers or interrupts the ongoing execution of our code. And our code quickly jumps to handle that lick or external interrupt. And after it finishing handling that, and it goes back to the main program and finish the rest and continue on the main program. So that is the code external interrupt. But what if we want to? But that's kind of event driven. That's externally driven. But what if we want to have two threads of programs that are both internally generated, and we want to sort of handle, execute or handle them at the same time? How can we do that? And then we have something called internal interrupts. So now I'm going to explain what are the triggers for internal interrupts. So internal interrupts is in most of the cases, if not all the cases, are triggered by counter timers. We know there's a clock for the microprocessor, and for Arduino Uno, it has a pretty slow clock that goes 16 megacycles per second. And in Teensy, for example, can have like 96 megahertz clock frequency. And so this is a clock, and there are counters in the microprocessors. Every time the clock ticks, which is a kind of very small fraction of like nanoseconds, every time the clock ticks, the counters count 1. And then the clock ticks again, it count another 1. Okay, so then what is a timer? So a timer is an internal event that's being generated once the counter reaches a pre-specified value. Counting of those counters is in parallel to our actual code. So that's kind of parallelization. And then when the counter reaches the limit we set, and it triggers an internal interrupt or timer interrupt. And then if you associate a function with that timer interrupt, and then that function will be executed at that point. Okay, everything up to here is kind of abstract. So that's why I want to use this interval timer as a good example for that. Okay, again, first, what's the problem we want to solve here? The problem is, the specific problem here is about synchronization. We do experiment often use multiple devices. So for example, here we want to synchronize the behavior data with the neural data. Then the way to do that is to send a TTL at the beginning of each trial to the intent, which is the EFS recording device, or to the PXI for the neural pixel in the neural pixel system. Furthermore, we want to do something more. We want that pulse to represent some information about the trial number, like which trial we are in right now. The way I represent the number is basically by how wide that a square pulse or TTL is. If it's 1 millisecond wide, then that means it's the trial 1. If it's 10 milliseconds wide, it's trial 10. But what if we have reached 1,000 trial? Then we will have a 1 second wide or 1 second long pulse. But if we just write for example, a digital high and then a digital write high, and then delay for 1,000 milliseconds and digital write low, and then it will block the execution of our behavior code by 1 second. And we certainly don't want to do that because the timings of the behavior is very important. We want to ensure that. So this is a case where we actually want to execute the two things parallelly. So on one line is just the main behavior code. All the timings should be guaranteed precisely. And then the other branch is like executing this pulse, going up and then going down. And here, a timer becomes very useful. So interval timer here. So I have a function number pulse on, and basically I just use the trial number as the input, and we can find this function in the utilities tab. And inside the function, there are only 2 lines. It does 2 things. So first, of course, digital write high, and then you see, oh, by the way, so you see here is a rig.number pin. So the rig class will define which number pin is, and here all the user need to know or need to do is basically write the rig.number pin. And basically we're going to turn that pin to high, and then we will set up the limit of the timer to be at this microseconds later. So the timer will begin counting right here. But this is another function. This function is called the number pulse off. This function will be called by an internal interrupt, this number of microseconds later from the background. So this timer is not going to interfere with the main code. Basically, the line 52 is executed in no time. And then the behavior code keeps going. Maybe the animal have started licking, and somewhere in the middle of the licking, time is up. Well, not the licking time is up, but the previously set timer limit is reached. And this function gets called just like external interrupt by the licking. But here, and what we are doing is very simple. We just digital write and to turn that pin to low. So maybe this is still kind of abstract, but the general idea is that, and here we fire up another thread, another branch of the code that execute at the same time as the main behavior code, and it sort of converges back when the number pulse off is called. Yeah, but of course this is just one example, and don't limit yourself to this. And there are a lot of interesting things you can do with that. Maybe just very quickly, here we use this tone function, but really for like triggering 400 Hertz or 500 Hertz frame triggers to capture individual frames from the high-speed video. And then basically this function is completely governed by a timer. So so every time the timer reaches certain values, start counting and reaches certain value, it flips the 500 pulse square wave, and it counts another period of time, and it kind of flips the voltage, and then flips the voltage, and then flips the voltage, and for every for each set interval by the timer. And we know for a fact that providing that train of square waves, it's not like interrupting anything about outdoor code, right? So that's another example like how a timer can be fired up and used to parallelly control signals. Okay, so that concludes the first part of today's tutorial, and the second part will be an exciting one, which is the Teensy audio system.
Can I ask one quick question?
Yeah, please.
I think in your satellites you had the include statements at the top for your internal library, or for your library. Is that right? So
yes.
So you don't, for this internal timer code, is that sort of something you already downloaded into the?
Yes, that's right, exactly. So the interval timer code is a part of Teensy Arduino. So if you look at this, the web page, so this is from the official Teensy website, and in this tree view, and under the Teensy Arduino, and under timing, and we have interval timer. So it's actually part of the packet, part of the system of packages Teensy has. Yeah, thanks for the question. So Teensy Audio Shield, and I briefly mentioned this as an example from last time. So basically, Teensy is just the brain Teensy cannot sing, Teensy cannot hear. So then, but we have the shield to give Teensy the capability to sing and hear. Although it's called audio board, but what is the nature of audio? So the nature of audio is basically a time series of analog signals, right? And if we have the capability to process, to handle the input and output of audios, then we'll have the capability to potentially to handle any kinds of analog signals. So this is why when Will proposed that we can maybe figure out some way to use the perch signal to detect the licking, and then the first thing came to my mind is maybe you try to use the Teensy audio system. In the advent of Teensy 4.0, things has become a little bit more complicated because now the Teensy audio shield has 2 versions. So one is, well, it has more than 2 versions, but some of the early versions are already outdated. But right now, the versions in service are 2. So one is a revision C, one is a revision D. And revision C is for the Teensy 3rd generation, and D is for the 4th generation. And if you see a Teensy board in the lab, they are all of the 3rd generation. And in fact, we haven't bought any Teensy 4th generation boards yet. But this is a hardware, of course, and the software is called the Teensy Audio Library. This is a very interesting tutorial, the official tutorial, and they basically all uses the audio examples for those tutorials. So I will pick some interesting examples, and we will quickly go through later. But right now, I want to jump directly to the example of how we use the Teensy audio shield in the sequence leaking task, because I think that's most relevant to experiments. Okay, so this is a finished code. I don't want to go into here because that's not how we write code, or maybe in this case I have to put quotes on the word write. In this page, Teensy Audio Library, and there's a design tool. And I will open the design tool in the new tab. And if you haven't done anything previously, you'll see a blank page here. You can certainly read more from the documentation and examples, but here I will just quickly go through how I build audio flow for the rig 1. Okay, so for an audio system, we have a controller, right? The microprocessor, and this microprocessor I'm talking about is not the one on Teensy, but the one in the audio shield. There's a chip processor for audio signal, and I can find that processor down here. Control. I know for a fact that the processor on the Teensy shield is this. So the reason we have so many controllers is because this Teensy audio library was not designed and only for Teensy. So the developer made it compatible with many kind of with several third-party hardware. So, but the one on Teensy is sendTTL 5000. Okay, so then we have the controller, and then now we need to think about how the audio information flows from the source side to the output side. So in some cases, it's like from input side to output side, but in our case, it can also be from source side to output side. Source means just any device or medium that generates audio signals. And in our rig, we have white noise. So we want to have a source that produces white noise, and we can find it. Can I find it? Oh yeah, here. The noise is here. Okay, when you click here, for example, it shows like which audio board or chip we're talking about or is associated with this controller. And here, when I can drag the noise components in, and it says, so this creates white noise. And in functions here, and we can use the levels argument to set the amplitude of the signal, and that goes from 0 to 1. Well, we want the system to be able to generate and produce noise, white noise, and if you like pink noise, so here is the pink noise. But also in my task, I use a pure tone as auditory cue. So pure tone is just a sinusoidal wave with certain frequency, and then there are actually more than one way you can generate that. You can use the sine function here. Yeah, this is I create a sine wave, but here I would do something more generalizable, which is use the waveform module. So you see on the right-hand side, these are all the waves that can be generated by the waveform module. And of course, you have a more generalized module, and that comes to the price of more complicated function specifications. So you need to figure out like what kind of waveform you want to do, and level, frequency, and amplitude, and for sine wave, offset, right? So when producing audio, we want the offset to be like this, like going from low to start, always like that, rather than sometimes from the bottom phase, sometimes from the middle phase, sometimes from the top. Yeah, and then there depending on the specific waveform you choose, there could be other things. And like here you can also see like where you can find examples of using this function, and the supported waveforms are here. So okay, so what else do we want to have?
Sorry, Manny, can I ask a question?
Yeah,
so
please.
Can you visualize the waveform? Like when you...
Oh, no, you cannot.
Oh, I thought they may have some function and you can see it, because sometimes when you implement it, and sometimes not exactly what you see.
Oh, yeah.
I mean, of course, we can record and then plot it, or I just wondering, is there any other way you can visualize it?
That's actually a very good point. I mean, I wish they enrich this web interface so you can have something like simulated waveforms and something like that. Yeah. But unfortunately, they don't have that now. And then exactly like you said, right now the way to test it is just to hook up a oscilloscope or into the recording system to see like how things are executed. Yeah. So fortunately, the things I'm doing right now are relatively simple, so I didn't need like too much verification for that. Yeah, but still, that's a very good point. Yeah, so we have noise, we have a module that gives out different kinds of waveform, and let's say I want some sweeping sound, right? Like something like do do do, sweeping sound, and here we can use the tone sweep to play that. But this is limited to a continuously varying sine wave, frequency modulated sine wave. Okay, what else? In ManyRig, our motors create some noise, and we want to have masking sound for the noise. And then the masking sound, in addition to the white noise, is the previously recorded motor sound, and just playing back randomly. So I recorded, I think, 12 different kinds of transitions from between different places, and then I'm like playing back randomly, selecting them randomly, and play back with also random intervals. At the bottom, we need the capabilities of playing audio files, right? And then the module that kind of reads the audio file and generate a sound is over here. Play from hardware memory and play from SD card. And here we can just so we kind of saved it into the SD card and inserted it in. The SD card was inserted in the audio shield rather than on the Arduino board. Although the like 2.5 3.6 has the SD socket on the Teensy as well, but we need to insert the SD card into the shield. Yeah, so we have this, and then let's just accept a different format here. You know, like you can save like, oh, they're the same. USD wave, USD raw, SD raw. Yeah, they're different format. The raw format or the .wav wave format. Okay, so those are all sources. We can have different sources, but you know the output is, we only have one output, right, from the headphone jack. And then let me find the output. So the output is not named. Output is actually named by the communication protocol that used by the output. So the output name is I squared S, I2S, I squared S. So this is nothing fancy about it. It's just, you know, like there are I squared C, there's SPI. SPI is the interface that Intel uses to transfer the spike data, well, to transfer the electrophysiology data from the head stage to the computer, and there are USB protocol, Thunderbolt protocol. They're just different names for the signal transmission protocol. And here Teensy uses I squared S for audio output. And now we're going to connect these to the output. Yeah, but here notice that a noise waveform tone sweep only have like one node out, and I can like pull a wire out from them, and but the wave file or the raw file, oh, not the raw file, the wave file is stereo because it has two. Yeah, it's a stereo, and the output of the Teensy is also stereo, so that's why it has like two input nodes there. Yeah, but that's just a side note. Going from here to there requires mixers. Mixers, and we can find mixers here. Yeah, so this is one mixer, and let's just get another mixer because we have more channels than we need, and of course we need to further mix them together. Okay, so noise goes to this, waveform goes to that. I'll just connect them sequentially. And here we cannot connect two to the same one. And here I go that. And this mixer goes to here, this mixer goes to that, and that mixer goes to there and there. So what we do here is we are funneling all the possible sources through two layers of mixers because one layer is not enough. As you can see by the number of allowed input. So we just use two layers of mixers and funneling into the two channels in to the output. And in the end, I used like one output to connect two, basically just to duplicate the mono to stereo, to like the one channel sound to a stereo sound. And you can still use one. It doesn't make a big difference. And then for folks who are familiar with this kind of mixing, or you often hear some sound like it's a remix of something. So it's basically taking components and then to mix them together, or basically to add them together with different ratios. For example, like if you set the ratios of these and that all to 0, but only the ratio for noise to pass through as by 1, and then what goes out eventually it's just the noise. And then if you increase the ratio for, let's say, the play SD wave, and then you are adding sound files into the output. So this is a command group that we found in the SeqlickSound viewer. And in the second tab is audio. Maybe you always wondered like what are those parameters are about. So here on the top of volume is, I think it's the, so I clicked the SGTL, the controller, and in the controller, and here we have a function that allows us to set the volume, the overall volume of the output. And then white noise, 100 means 100%. This actually corresponds to the level being 1. And then waveform 1, which is the tone frequency, and the motor 1 is like basically the gain for this, and we set it to be 1. And here, these 3 tabs are basically the ratios of mixing. And so these 4 values correspond to the 4 nodes here, and these 2, the 4 nodes here, and the last 2 correspond to the 4 nodes there. And then to calculate the final proportion of each component, so you have to trace the wire. So for example, it goes here and goes there. So that's the mixer 1, the first field of mixer 1 and the first field of mixer 3. And you times the 2, and that gives the final ratio of the sound. So this really allows you to fine adjust different proportions in your final audio output. So after drawing this, we're going to transfer this into Arduino, and the way to do it is very easy. So here you see the export button, and you click that, and it generates the code for you. So here on top are everything you need to include. It tells you to include, and here, like it basically initializing all the modules we saw in the graphical user interface, and as well as like how they are connected together. You see the patch cord is connecting different things together. We just copy that, and then we go to the audio thing. So here I'm pulling out a finished program, but you can see like the top part here were like directly copied from the design tool. But that's not the end. So these are this only describes the hardware configurations or the software implementation of the hardware. But in the code, we still need to write the logic, right? We need to specify like what are the file names that we stored on the SD card, and then what pins we use to are used by the Teensy audio shield. And then I'm actually using a satellite object for communication between this Teensy and the computer. Oh, by the way, in the setup, I just set up the hardware, set up the port, and set up the initial volume, and set up the initial noise amplitude, frequency, and initialize the mixer gains. And nothing really special about that. Initialize the or trigger pins as input. So trigger pins is about behavior. Trigger pins is not about like this audio diagram or anything. And for example, here I use one of the trigger pin. I actually forget which trigger pin. Maybe the first trigger pin. I use the first trigger pin to control the play of the pure tone. If you are interested, you can like go to the details, and this is the portion of controlling the play of pure tone. And then my rule is, as long as that pin has a high voltage, and then we just keep playing the pure tone until the voltage of that pin drops back to 0. And here, like before each play, I kind of reset the phase and amplitude and so forth and so on. And of course, we have a reader. So the reader is what implements the communication between our computer or PC with the Teensy. Here, I just want to put out some teasers to say like to really show like what are the potentials of this library. And here I will only show a few examples. First of all, the signal not only can be generated by the SD card or by some waveform generator, but it can also come in from an I2S port, which is actually the microphone on the Teensy audio shield. Teensy audio shield has has accept microphone input, and then actually in this case is for example, we can provide the perch signal into the input, or maybe not through the microphone jack, but through something called the line in jack. So this example is about Fourier transform. So the audio shield can do real-time Fourier transform of the input signal. Yeah, you see it has several input: play SD card, play from memory, waveform. So, and it goes through a mixer, and then it goes out to a FFT, fast Fourier transform module, and with a certain resolution, I believe. Yeah, and you see here, so it's printing out the result of Fourier transform, and then of course you can access that information. So then, how is it useful in neuroscience experiment? So what I can think of is the real-time control of optogenetics in sleep studies. For example, we can use FFT to detect whether the animal is in like REM sleep or non-REM sleep, and together with EMG, together with EEG and EMG, and whenever a certain frequency band reaches a certain threshold, and then it triggers an optogenetic stimulation to a certain brain area. I mean, if you just hear about that, it sounds like a super fancy and complicated setup. But how amazing it is that you can actually implement the whole thing, just use Teensy audio system. Yeah, and another thing is that we can also do neuronal spike triggered stimulation. And for example, here we can use this peak detection. Yeah, so we have some audio source, or basically a signal source, and then go to peak detection module 1 or peak detection module 2, and you can draw a threshold, and whenever there's any kind of peaks, or in our case, action potentials passing through that, we can trigger a kind of stimulation. All right, so those are just some teasers, but at the same time, I have to point out kind of pretty serious limitations of the Teensy audio system. And the first limitation is the temporal precision, or to be more specific, I should say the temporal accuracy. So this diagram, like processing from one end to another, takes time, right? And especially for audio signal processing, you need some buffers to store some waveform and then play out the buffers. And then the delay, at least in my case, is around 5 milliseconds. So that might be a kind of big delay for neural data. Well, it's probably fine for EEG, EMG, 5 milliseconds, but for spike-related thing, that might be a challenge. But for Will, like if you use it for like the leak detection, I think 5 milliseconds is something very acceptable. I'm not saying like the detection has a delay, but the processing need to compute and analyze, and that thing may take time. And the 5 milliseconds is right now is the time that I measured in this case. But if you add in like Fourier transform and others, that time may increase, and it's really something we need, one needs to test it out in a case-by-case manner. And then, so the second limitation is the frequency range. So this audio system comply with the DVD, I think the DVD standard, so which is 16-bit resolution and 44 kilohertz. Oh, that's not a DVD, that's a CD standard of 44 kilohertz. So that's a sampling rate. But we know that the mouse can hear way higher frequencies. So if you want to provide some ultrasonic sound, you have to say bye to Teensy. That doesn't give you that. But the thing is, you know, the white noise audio file that we play in all the rigs, including Eating's rig or our rigs, do not have anything higher than CD frequencies. So although Dan bought the speaker that's capable for, well, Oh, I take that back. Like even the speaker we have doesn't go above that frequency. So I guess for us, the specs for Teensy regarding that is fine for now. Okay, so that's the end of the Teensy system, and I think that the time is not too bad. The next will be about the ZaberMotors. I'll be quick on that. I mean, of course, we have expert here, which is Linhua. So Linhua, please correct me and share with what you know, if you like. So the first thing is we bought a set of expensive Teensy setup, which usually includes, if you start from scratch, then that means it usually includes a controller. For example, here it shows the XMCB2 controller, and as well as a few motors. And the first thing you want to do, and which people often forget to do, is to get your controller know your motors, because Zaber only have maybe like a few models of controllers, so they are designed to be general purpose, but not general purpose. They're designed to work with many motors and stages from them, but the controller out of the factory doesn't know like what stages you are using. Especially here, like we have the two-axis controller, and I believe XMCB2. Two stands for the two axes. And then if you have two different stages, and you also the controller also needs to know like what stages are what model of stages are connected to each of those controlling channels. And so to configure that, you need to download the Zaber console software, and then connect your controller to your computer, and let the console to recognize that controller, and at the same time connects your stages to the controller. So there's a place that allows you to specify what stages you are using, and try to be very specific to the models, because like different revisions of the same stage may have like different currents and different sorts of specs. So yeah, just to make sure you kind of configure that. But this is a one-time configuration. Once it's set, and as long as you don't change like the pairing of controller and motors, and it will remember that forever, even if you power it off. Although ZaberMotor stages can be controlled by the knobs, we predominantly want to use software to control the movement of ZaberMotors, right? Either, well, usually in our case, it's just Teensy. And the all communications require some sort of protocol. And we are communicating in a protocol called English. And the satellite system uses this also kind of some sort of protocol. I call it satellite protocol. And so this is the one of Zaber's protocol, and I think it's the main one. It's an ASCII based protocol. And without getting into the details here, I'm just showing you one example of how how a message looks like. And so this is a message, or a command. All commands start with this / and then one, I think it means like all device is basically a kind of addressing, indicating like which device I want to apply this command to, and this is a command name. So I want the stage to this stage or stages to move, and this providing additional information about like how the move should be implemented, and this is like moving by the absolute coordinate, and the last one is just the value of how far we need to go. So, each field of this command or the string is delimited by space, and you remember the satellite viewer commands were delimited by comma, although you can actually set the delimiter to whatever you like. If you want to communicate at this level, at the very low level, and this is the reference page you want to go to. despite that the Zaber is such a powerful and system with many rich functionalities, and what we end up using in experiment is just a handful of them. And in that case, it's actually easier if we write some libraries just to streamline this process, rather than us like in our code combining, forming those strings and then do the hard work. So by the time we were using ZaberMotor to control, we use Teensy to control the ZaberMotors, there weren't any libraries available. So that's why we wrote our own. But later, Zaber released their own library. So they actually released more than one, but the first one is kind of useless and badly designed. And I think this one is better. And so you can even download this library directly from within Arduino IDE, which is used as a library manager. And let's just try that. Include, oh yeah, library manager. Yeah, we try Zaber. Yeah, you see, we can actually find that. So things become a lot easier. See, like, so here include Zaber and Zaber ASCII, and then you just create an object that represents the controller, tell the Arduino which ports through which we're communicating with the controller, and then we send the home command to the device represented to 1 or device 1. Yeah, so this is basically a wrapper that, not wrapper, like something to implement the kind of the text strings here.
Hey Manny, I'd like to add a point. Can you just go back to the previous slide you just showed?
This?
Okay, never mind. So on the website, it says it's recommended using or buying a shell which is compatible with Arduino board. But actually, we don't need to buy that shell. We're using the Teensy board. So we just need to change the object name. It has an object name ZA, Zaber, and there's a serial number following it. And we just need to specify the serial number, and that's fine.
Yeah, right. Yes. So in Teensy, we don't use the serial. We use like serial followed by a number, like 0, 1, 2, 3, 4, 5, 6, things like that. And then you can find the corresponding information from the cards, I'm showing. Yeah. The more specialized a library is, the easier the life for the user, but in the cost of flexibility, right? The Zaber official library is quite minimal, and it still preserves the structure mostly about the original ASCII protocol, but that again requires you to spend the time learning it and learning the protocol and how to drive it. The library that Yuxi and I wrote, yeah, so this is a library what we originally designed, and then yeah, so in Arduino code, we have a ZaberMotor class, and we create an object that represents the controller, and then we use a serial 3. So that's almost exactly like how we initialize using the official one. But the functions in here are no longer like send command or something. So they are already, the function name suggests that they already implement certain commands. So I would divide all the functionalities into maybe 2 parts. So the first is about configuring the motor. Oh, by the way, again, we are looking at the C++ header files. Header file gives you a very nice summary of what are the variables and functions being defined in this class. Here we set what are the maximal positions for each axis. Oh, yeah, sorry. Forgot to say, this class supports up to 2 motors. So Zaber only have like controller controlling up to 2 axes. So that's why I chose the number to be 2. But of course, with this class, you can also implement a controller. You can also use it with a controller that only has 1 axis. For the same reason, we don't know what kind of stages we are connecting to, and that's why so there are some properties that we need to tell the Teensy, like what are the max position, and also like its reverse means like which side of the stage we want it to be 0. So normally, as the side with the motor is a coordinate 0, the side without the motor is the maximum distance, but we can flip it for our convenience. We can also set the reference in the middle of the axis. Jitter is something about experiment. So what Dan told me was that when they were in Geneva, they were testing the ZaberMotor, and they found whenever they drive the motor to a given position, the noise that the motor creates are exactly the same. It's position dependent. And they didn't want the animal to use the same sound as a reliable auditory cue to solve the task. So that's why they want to create some jitter. So sometimes there are few microns away from where they want to go. Sometimes there are few microns behind where they want to go. So a few micron differences doesn't really affect how the doesn't affect the kind of the behaviors because it's only by microns, but it kind of changes the sound profile. And you can set the maximum speed and then set the acceleration of the motor. And this command homes O the axis. So 0 means O axis, and 1 means the first axis, 2 means the second axis. And okay, so and so far these functions or properties are all about configuring the controller, configuring the stages connected to the controller. And the second half of this is about movement. Move function moves one axis at a time. For example, you just tell which position to move to and what axis to drive. By default, the first axis. And stream, for example, streamline gives you a coordinated motion of the two motors. So for example, like if you want to go obliquely, the distance for position for the first axis to travel is greater than the second axis to travel, then the Zaber controller will decrease the speed for the second motor so that the first and second arrives at the destination at the same time. And the vector sum of the speed like matches the acceleration and the speed settings here. And this is a coordinated motion to go for a line, and here are coordinated motion to go for an arc or go for a circle. So just different wrappers that's available in the Zaber ASCII library that directly provided for the user. So the users who use this ZaberMotor library doesn't really need to know the ASCII2 library. Yeah. If we look at the implementation here, I have created some default value for the max positions. And these default value is kind of specific to the setup I use for the sequence leaking task in Rig 1. But that really shouldn't stop you from just going in there and change these values to match whatever motor you use. That's almost it. So the last is a quick note on stream arc function or the related. So for example, stream arc 2 asks for your starting position x and y, and then the end position x and y, and it goes an outward arc, like between the two directions, just like what we see in the backtracking transitions in the task. The starting position has to be the position you are physically are. So for example, if you are at position like 100 and 200, if you are physically at 100, 200, and you want to go to 300, 400, and then you can go there. But if you are physically in 100, 200, but you want to, but you tell the controller to go from 0, 0 to 300, 400, then you will crash the system. I think they should have handled that. I think it's their poor design. It shouldn't crash it. But just a note on that is that if you do that, you'll crash it. So this is hugely related to our training, because during training we want to play with how far the lick ports are from the animal, and then also like kind of the translational positioning of the lick port of the set of lick ports. But if you do that, if you change that, then there will be a mismatch between the specified locations versus the actual physical locations after you kind of change your task parameters. And then if you do that, and while using the arc, or when the system is just trying to use this, and you'll crash it. And the only way to resolve that problem is to do a home and then restart everything. So then does that mean like if you use the kind of arc motions a lot, do we have to kind of stop the task and then change it and then start again? Actually, no. So there's a trick to circumvent that. The trick is you pause the task so that you have time to operate, and then you change the task parameters about the position, and then you have to know like which position you are at the moment. For example, like the position index 0, position index 1, position index 2, and you just manually click the P0 or P1 or P2 or P6, and to kind of to make the physical location to be the same as the designated location. And then after changing that, and then you resume the task, and then things will just continue normally. But that's a pain. I hope there's a better way to address it, but it is how it is right now. All right. So lastly, this is something quite specific to the task. You know, the ZaberMotor has a Cartesian coordinate, x and y, but the best coordinate for arranging the lick port with respect to the mouse face, with respect to the tongue, is actually the polar coordinate, and with the angle and the radius. And then we often need to kind of go back and forth between the two coordinates, because on one side is how we set it, on the other side is how we need to tell the ZaberMotor to implement the motions. And that's why we have another class together with this ZaberMotor class. It just includes the ZaberMotor. It will have both included. So you can set the x coordinate of this of a position object and y, or set a or r, and then the change of the xy coordinate will automatically update the coordinate in a and r. Well, sorry, a for angle, r for radius. Yeah, so the two sets of coordinates are always linked and being maintained consistent internally in this object. Furthermore, we know that if we have an x coordinate, two x coordinates, and we can do addition, subtraction, and then basically we can do vector subtraction and vector addition. And this position class also allows you to add two positions together or subtract two positions. And basically, it kind of performs the vector operations for you. Yeah, so in the code here, here you see like here we have a list of positions, and position here we set a resting position, and then we just have like we use like this kind of position class everywhere in the code. So I think it's worthwhile explaining what they are and how they work. And that's the end of the of this tutorial and the end of the series. Yeah, thank you.